Hi, this is part 2 of section 1.5 graphing techniques using transformations. Last video we ended with reflections. Let's go ahead and continue with vertical stretches and compressions. Suppose you have a parent function f of x and there's a constant in front of your parent function. Then there is a vertical stretch for absolute value of c greater than 1. But if that constant is between 0 and 1, then there's a vertical compression. Notice here that let me highlight this so you can see it. I do tell you what or how the point xy shifts for vertical stretches and compressions. So if your parent function has the point xy, then your new function has the point x comma cy. If you look at example 7, we have our constant 3 and our constant is greater than 1. So because it is greater than 1, we have a vertical stretch. I'm just going to write that here, vertical stretch. If I were you, I would take some time to read the definitions. I've actually put them down here so you know what is it that your graph is going to look like, whether it's going to stretch, compress. You can read the description and hopefully you have the notes in front of you so you can press pause if you like. Okay, back to example 7. I find that it really helps me to write the points of the parent function and then shift them from there. So one of our points was 1, 1. And our new point is going to be 1 comma our value of y times the constant. So our value of y is 1 and our constant was 3. Therefore, our new point is 1, 3. We also have the point 2, 2. We have the point 3, 3, 4, 4, and so on. So you can use as many as you like or to as many that will help you graph an accurate function. Okay, so x stays the same, and then we just multiply our y value by 3, which is 6. So our new point is 2, 6. Let's go ahead and plot 1, 3 and 2, 6. I didn't label these. I should have makes it a little bit easier when I'm graphing and I don't have to count. Okay, so we have our vertical stretch here. And because this is symmetric with respect to the y-axis, I don't have to find the other points. I just know exactly what they look like. We have y equals 3 absolute value of x. Okay, now let's look at example 8. Notice here our constant is between 0 and 1. Our constant is a half. Therefore, we have a vertical compression. Vertical compression. And I'm going to do the same thing I did in example 7. I would just take the points of our parent graph and then see how they change. So x stays the same again. As for y, we're going to multiply y by 1/2. And of course, always simplify. And then the other point was 2, 2. And again, x stays the same. I'm actually going to zoom in on this problem. X stays the same. Oh, I just wrote x. Our x stays the same, which is 2, but our y value, we're multiplying it by our constant. Therefore, we get the point 2, 1, because a half times 2 is 1. And let's go ahead and plot those points. So we have the point 1, a half, and we have the point 2, 1. And then our new graph looks like so. And then again, this is symmetric with respects to the x-axis. So I'm just going to do the exact same thing on the other side. And that didn't come out too well. Try that again. Okay, that's much better. And that is our, just like in class, always going to the home screen. And that is our y equals a half absolute value x graph. We also have horizontal stretches and compressions. If our constant is in front of the x value, then we have a horizontal compression or a horizontal stretch. If the absolute value of the constant is greater than 1, we have a horizontal compression. If it is between 0 and 1, we have a horizontal stretch. For both of these cases, the y value does not change. And I'm referring to our parent graph. Our parent graph is xy. So when we have that constant in front of the x, the y value does not change, but our x value does. We divide by our constant c. So notice here that our c is equal to 2. Therefore, since 2 is greater than 1, we have a horizontal compression. And I'm going to do the same thing I did for examples 7 and 8. I'm just going to take the points of our parent function, which is y equals square root of x. And this time, I'm going to take the x value and I'm going to divide it by c, our constant. And again, the y value does not change. Let's take the 0.42. And then we're dividing for our x value by 2. And let's go ahead and simplify that. We get the 0.21. We're going to plot our new points. We have 1/2 1. And we have the 0.2. Sorry, I apologize. I forgot to leave y by itself. That was an error on my part. So this should be right here. This should be 2, not 1. But it's good that we do these mistakes so that you can see that it wouldn't have made sense to have the 0.21 on my graph. 0, 0 still there. It doesn't change because if I multiply by a constant, it's still 0. So we have 0, 1, the 1/2 1, and then the 0.22. And that's our new graph with a horizontal compression. Okay. Now let's go on to example 10. Notice here that my constant is between 0 and 1. Therefore, we have a horizontal stretch. Okay. Once again, I'm taking the parent function's points and I'm going to divide by my constant. Now, in this case, x is 1 and our constant is a half. So that looks kind of weird. We do have to simplify that. And notice the y value does not change. Now, dividing by 1/2 is the same thing as multiplying by 2. So we have 1 times 2. And then we have the 0.42 of our parent graph. We're going to take 4 and then again divide it by 1/2. And the y value does not change on our parent graph. And again, dividing by 1/2 is the same thing as multiplying by 2. So we have 8, 2. And let's go ahead and plot those new points. 8, 2. And there we have our new function. Now you try. So I have a few examples here. what I'd like you to do is I'd like you to pause the video, work these out on your own, see if you can graph all of them. And once you're done with all of them, that's when you can press play again and check your answers. By the way, I did say here, note when you have a reflection and a shift, always do the reflection first. If you don't do the reflection first, you will there's a possibility that you can get the wrong graph, the incorrect graph, because of negative values and whatnot. Oh, and when you have a stretch and compression also, it's better to do that one first before you do the shift. Okay, go ahead and pause the video and try these problems for yourself. Hopefully you did try all the problems and you're coming back, and now you're just going to check your work, and you can press pause if I am going too fast and you need to see the answers. I tell you exactly what I did. So not only do I show you the graph, for example, in A, I did say graph of y equals x cubed shifts up by 4 units. And I drew the parent graph for you. Where they get a little bit more complicated, I actually did the shift first and then the compressions, like in part C. And then we have D and E. And finally, F and G. Thank you, and that concludes section 1.5.